Hello and welcome. This video is a demonstration for our audio pattern detection project. I'll be walking you through the Python code in VS Code that solves this complex engineering problem. The objective is to design a system that can find and count a specific word in a long audio file. To build this system, we're using several modern libraries. We import Librosa for advanced audio processing, NumPy for fast numerical operations on arrays, SciPy for its powerful signal processing functions like peak finding, and Matplotlib to visualize our results. The first step in our algorithm is pre-processing. This line, yTarget equals librosa.loadTarget file, SR equals 16,000, uses the Librosa library to load our target wave file. It returns the audio as a NumPy array, which we store in the variable yTarget. By setting the argument SR equals 16,000, we are explicitly telling Librosa to resample the audio to 16 kHz. This is a key design choice for both efficiency and to focus our analysis on the frequency range of human speech. Next, we move to the core of our methodology, feature extraction. Instead of working with the raw one-dimensional audio array, we transform it into a two-dimensional MEL spectrogram. This line performs this transformation. It takes the audio data and applies a short-time Fourier transform to analyze the frequency content over time, creating a spectrogram. It then maps these frequencies to the MEL scale, which is based on human pitch perception, making our features more robust. Then this line converts the spectrogram's linear power scale to a logarithmic decibel scale. This is important because decibels align better with how humans perceive loudness, which helps distinguish features more clearly during matching. In the pattern matching phase, we implement a sliding window using a simple Python for loop. This loop iterates across the target spectrogram from beginning to end. Inside the loop, this line uses NumPy's powerful array slicing. It efficiently extracts a small chunk of the target spectrogram that is the exact same width as our template. The next line is where the comparison happens. We perform an element-wise multiplication between the window and the template, and then sum the result. This is a fast and effective way to calculate a correlation score, which we store in our similarity scores array. Finally, in the detection phase, we analyze these scores. This line uses the findPeaks function from the SciPy library. We pass it our similarity scores, and it finds all the peaks. The threshold argument is critical. It tells the function to only consider peaks that are higher than our specified threshold. This is how we reject noise and avoid false positives. The distance argument prevents detecting the same word multiple times. This entire process of tuning the threshold is a key part of the engineering investigation. Now that we've walked through the code, let's run it. Output here in the terminal. It loads the audio files and completes the feature matching very quickly. The script now generates this plot. The top graph shows the audio waveform with our detections marked by red vertical lines. The bottom graph provides the evidence, showing the similarity score over time. The red X marks the peaks that successfully crossed our threshold, confirming our detections visually. As soon as I close the plot, the script prints its final results to the terminal. As you can see, it reports the total number of occurrences found and then provides a clean numbered list of the exact timestamps for each detection. This successfully fulfills our project's main objective. Thank you for watching.